DPR Construction, a national construction company with offices throughout the United States, needed a new location for their regional office in Phoenix, home to 110 employees. Selecting the site was the first step in developing what would become a living lab for sustainable construction practices and renewable energy generation. The overriding objective was to find an underutilized existing building in a highly accessible redeveloping area of Phoenix, close to public transportation, that DPR could transform to benefit the community's redevelopment efforts. The unlikely selection was a shabby building whose checkered past included being an adult boutique.
During the design phase, what I really wanted to do was inspire the design and the development team to think outside the box, and because we knew that we were going to do something different, and not even just outside the box, but beyond the box, and challenge them to take things to places that they'd never been before, because we didn't want to just repeat what other people have done. We wanted to try to find new solutions to old problems.
So it was an empty retail space. It's a block, square, empty box. So it really lent itself to really any type of design and renovation we wanted to do. It didn't have a lot of interior columns. It didn't have a lot of interior walls. So the demolition in order to turn it into what we turned it into was really minor. The location was also key. So it's in the middle of the Discovery Triangle in Phoenix, which has a great connection to the airport, a connection to Tempe, Scottsdale, Phoenix. So all of our partners and all of the cities that we work in, this was a really great location.
We have the light rail there and the SkyTrain, which services the airport, which means that people that come and visit us and fly in don't even have to get a cab or a rental car. They can fly in, take the SkyTrain, and walk right into our office. It's really fantastic. We have bus service. We have access to every major freeway within, I'd say, at least a half a mile. So access to and from the office has improved for all of our staff, because we tend to be a bit mobile. Our people have to come and go from the office quite often, and so it's nice that they're able to get in and out of the office quickly. Our old office on 32nd and Camelback was a very nice space and a nice area, but it meant that our people had to spend 10 or 15 minutes on surface streets before they could even get there. And it became prohibitive for them to come and go, and people would avoid coming to the office late in the afternoon to avoid that traffic. And so this really posed a lot of great benefits to our folks.
Well, the project is about a little over 16,000 square feet. Really interesting project in its size, because we don't see, in my experience, we do a lot of office buildings. You don't see office buildings of that size, and that's because this really isn't an office building. It's a retail building that has been renovated to become an office building, and I think that's quite interesting in that there's a lot of buildings like this in the metropolitan Phoenix area, and I'm sure in a lot of other large suburban scale cities where these buildings are underutilized, they're abandoned. And I think this is a great example of how you can take an existing building that may not have a life as a retail building, or it's blighted, and it can be converted into an office building, and it can be converted into something that's very energy efficient and LEED Platinum and net zero and all those great things.
The DPR regional office illustrates the unique opportunities that can arise from an integrated team working together to find synergies. With a fast-tracked 10-month design-build schedule, ideas needed to be suggested, critiqued, and decided upon in short order. All stakeholders were engaged early, including key subcontractors, commissioning agents, and energy consultants. From the outset, DPR established the goal of meeting net zero annual energy use. In addition, all strategies that met a 10-year return on investment would be included. As part of their effort to improve energy performance, the team put all approaches on the table, including challenging the U.S. norms for the rigidly air-conditioned office.
We started off the project with 10 goals in mind. In fact, every time we had a design meeting with our architects and all our design partners, we put these 10 items on the board, and we made sure that we kept going back to these items throughout the design and construction process to make sure that we were achieving all 10 of these goals. And so the goals were: 1, net zero energy over the course of the year. 2, it was bring the outdoors inside. We didn't want to look out our windows and see asphalt. We wanted to look out our windows and see greenery. we wanted the office to feel less office-y. I think we made that word up, but we know we achieved it when our first day of operation, somebody walked in the front door thinking that it was a coffee shop, not a construction company. So yeah, we felt pretty proud that day. A couple of the other goals were passive cooling. We wanted to make sure that we were utilizing passive cooling techniques like evaporative cooling to cool the space, so we're not using so much energy. We wanted to have a 10-year payback period on everything within the building that was a premium over normal construction that we built into the design to make it a very efficient building. We wanted to showcase our talents and our culture within the architecture of the building. We wanted to treat water as a precious resource. Obviously, we are in the desert Southwest, and water comes at a premium here, and we don't want to squander it. We wanted it to be a safe place to work, and there's a couple features around the building you can see that serve dual purposes, such as security and just beauty. And we wanted to change the marketplace as well. We wanted it to be a showcase. We could bring architects through, we could bring owners through, that incorporates a handful of really unique design features that work in Arizona that they can apply to their projects.
And sustainability isn't just about achieving that LEED standard. That it, again, is an indicator of good design and good construction practices. And that's what we were shooting for. We felt that if we could create a facility that could operate in the desert climates, and achieve a net zero result, which means that we were creating more energy with our systems than we were using in an annual time period, then we would achieve our goal, because we knew that by doing that we would have to accomplish the LEED requirements. So our primary goal was to be net zero, and then on top of that, whatever LEED certification we could achieve with that design is what we were looking to get.
The project is an existing building built, well, the first portion of the building was built in the 1960s, was renovated sometime in the 80s, and we're not sure exactly what date that was, to its current location. It's a 16,000 square foot project located in Phoenix, Arizona, which is in climate zone 2A, which is a hot, dry climate.
So you have this huge city with an incredible amount of pavement and concrete. And so we have heat island effect, and it is not uncommon that in the summertime, at night, in the evening, it won't get below 100 degrees within the city. And so that is a real problem, not just for buildings, but for urban, our urban form and the cities we live in, makes it rather uncomfortable. So, whereas in the past, you look at it from a historical standpoint, from a building technology standpoint, prior to air conditioning, et cetera, people used to design buildings with thermal mass. The buildings be able to be opened up at night, and they could bring in the colder, cooler breezes, cooler temperatures, and the interior of the building would cool off prior to the next day when the building started to heat up again. You can't cool off a building when it's 100 degrees outside at night. So some of the things that we have to think about go well beyond what some of the historic precedents are for designing buildings in this region and in this environment.
The desert provided a challenge for us, and also we have things called monsoons and certain storms that come up in the summertime. And we're talking about buildings with certain features, operable windows and solar thermal chimneys. We had to be cognizant of that as well. So designing and constructing a building of this type with the parameters we had, the desert did prove some challenges.
This being the second office that DPR had constructed for zero net energy, we had used a lot of our background information developed in the first building in San Diego, and we had taken a lot of concepts from the San Diego experience and transported it to Phoenix. Of course, it was far easier to design a naturally ventilated building in San Diego. We really only had to open windows, versus the design here was a case of having to develop a thermal chimney, develop the passive shower towers, along with the operable windows, so that we could extend the thermal comfort zone for the building.
So before the project started, in terms of thermal comfort, we came from an office that was a pretty typical office. It was very cold all year round. There wasn't a whole lot of thermal comfort options. It was just the temperature was going to be what it was going to be. So it was 110 outside, and it was still going to be 64 inside of our office. So surprisingly, people were really excited to move into a space that was going to be a little bit more realistic and mimic what was going on outside more than just being 65 all year round. We had all been used to just having to wear long sweaters and coats in our office, even if it was in the middle of July in Phoenix.
Prior to this building, all of the environments I worked in were heated and cooled as most buildings are throughout the United States or the world. And in Arizona, of course, in the summer, it's extremely hot. And the buildings tend, no matter where you go, to crank up the AC, and it becomes cold. And so you're going from this extremely warm, hot outside of 100 degrees into a cool area, and you have to, it's a drastic change in body temperature, and you usually, many people will carry a sweater or something when going into these environments.
We started the design of the project, we didn't even know exactly what we were trying to do, except for we wanted to be net zero. We knew that we wanted that. But in working with our design partners of Smith Group and Kima Engineering, we realized that there were a multitude of ways that we could achieve different strategies. And those strategies led us down the path that we ultimately followed, which was a passive cooling system, which means that we're using airflow to help cool people even at a higher temperature. So we operate well outside the normal of 72 plus or minus 2 degrees in our office. We operate from 68 to 83 degrees as our standard range of occupancy. That means that we won't turn on any air conditioning until we cross that threshold of 83 degrees, and we don't turn on any heat until we cross the threshold of 68 degrees. We knew that that would pose challenges because it's different. And anytime you change things for people, you change their world, it changes how they feel about things. So it was important to us to address that early. And so even before we were finished with construction, we started a PR campaign to let people know what we were doing, let them be part of the process. We informed them of the things we were trying to accomplish and how we were going to achieve those things so that they could be part of the solution. We wanted them to be aware of their environment changing before they got there, that the lighting system would be automatic, that we were going to operate with little to no lights being on during the day, that we wouldn't have air conditioning running all the time. It was going to be more natural ventilation, which meant that there would be challenges with that. Noise and dust from the outside air coming in meant that we had to clean more often. The sound would be different in the office.
The project's main goal is to achieve net zero energy. The most important first step is to reduce the energy demand of the building. There are 3 main areas the team focuses on in order to reduce the energy load: an integrated passive system, lighting, and occupant engagement.
So we've reduced our lighting load significantly by installing tubes and really not having lights on during the day at all. We've reduced our mechanical loads by having a passive cooling system as our first line of defense against the Arizona heat. We've reduced our plug loads by having a vampire switch that shuts down all non-critical loads at night.
At our first design charrettes, we realized very early that net zero could be achievable for us because we had done some very early analysis on DPR's existing buildings. We had a good energy profile of the way that they operated. And we knew that they were a very proactive client. So setting a zero net energy target was one of the very early goals, and that drove many decisions. It drove the decision for natural ventilation. It drove the decisions for natural lighting. It was one of the central goals that DPR recognized very early.
In order to dramatically reduce the energy load, the team commits to creating a building that is passively cooled for as much of the year as possible. This is a radical approach for a commercial building in the Arizona desert climate.
Passive cooling is cooling without any mechanical means or methods. No motors, nothing reciprocating, nothing moving electrically. It's just passive. Like the wind outside, it's passive. There's no mechanical means behind it.
My main vision from the project was to deliver a design that would allow us to maximise the natural ventilation. We did some early analysis that showed that natural ventilation in the Phoenix region would probably be effective for around 24% of the operating hours of the building. That's not a great percentage, and hard to justify the cost for natural ventilation at that lower percentage. So my goal was to really strive and design a system that would allow that percentage to increase. The goal of something around 36% of the time using natural ventilation is what we strive to do.
Our passive cooling and heating system works with 4 main components. We have our shower towers, we have our operable windows, we have our fans over our workstations, and we have our solar chimney. All 4 of them work together with a very robust control system. They're all very ancient technologies, obviously. Evaporative cooling, just wind blowing on your skin, and hot air rising, but they all work in conjunction.
So the evolution of the I'll call it the passive cooling system, which encompasses everything, because without one, it really doesn't work. It's all one system. And so, understanding the sequence of operations, which you really have to develop how you're going to run the building before you decide what system you can construct and operate. We had to understand that the primary concept was to move air, and moving air meant whether it was coming through the windows horizontally and vertically out the solar chimney, or if it was air that we were holding in the building and circulating with fan systems that would ramp up at a slow speed as we're trying to cool, and as the temperature rose in the building, they would gradually speed up to just maintain that fine cooling point for us. It's about the sensible cooling is what we call it, is how you feel when you're in a nice cool breeze or under a tree on a hot day with the wind blowing. It's much cooler than standing out in the direct sun.
The 4 main components that work in an integrated fashion are operable windows, thermal chimney, shower towers, and high-volume, low-speed fans.
We incorporated passive cooling and heating on the project. And we also augmented this with some conventional heating as well and cooling as well. So we have a solar thermal chimney on the roof that acts as a large heat sink. It's actually clad in zinc. And the conventional engineering is that hot air rises. Well, when that rises, we have dampers on the solar thermal chimney that will open up and hot air will go out. In the passive mode, you have to have air to come in to allow air to relieve. So we have shower towers outside, which are nothing really more than a large round vertical section of evaporative cooling. There are some shower heads and misters in there, and as the water tumbles down, it cools the air that is then drawn through the building through the solar chimney. The buffer between that are the operable windows on the building that are commanded by the control system. So between the passive cooling and heating, the operation of the windows, depending on the temperatures in the building, morning, evening, occupied, unoccupied mode, winter to summer, the building just works in concert with all those parts to make it become efficient. On some of the warmer, very warm summer days, we also have some conventional systems on the roof. We have packaged heat pumps, again, direct expansion units on the roof. But we have very few of them and very small tonnage of them. If I remember the original block load, the building was just over 60 tons. I think we have 32 or 33 tons on the roof that serve the large area of the building. And they work again in concert only when needed on the very hot days or very, very cold days when we can't achieve what we need through the passive systems. Also at the periphery of the building on some of the office rooms, we have what's called a VRV system. It's a variable refrigerant volume system. There's a condensing unit on the roof, and has a series of indoor units that make up small air conditioning units for those areas. Very small tonnage, 8 tons there to speak of. Predominantly, the engineering behind it and the thought behind it was, let's have a building that can normal operate without any conventional means, passive means to say, between 64, 66 degrees, 68 degrees, and 82, 84, and maybe even pushing the envelope on 86. So that's a large delta T, a large change in temperature.
The project incorporated 87 operable windows along the building's east and north facades, providing access to fresh air and natural daylight. Controlled by outside climatic conditions, they open gradually to adjust to ventilation needs of the space.
Our passive cooling system has 4 main legs. The first leg is bringing the outdoor air inside through our operable windows. We have operable windows on the north and the east elevations of the space. They operate on actuators. They open when the temperature outside is the temperature we want to bring inside. So obviously in the wintertime, if it's too cold, we don't want to bring it in. In the summertime, if it's too hot, we don't want to bring it in. But they open at the right times. When they open, the fans that are over all the workstations in our open office space, those turn on as well, just to create evaporative cooling on your skin. We don't care about what the air temperature is in the space. We care about what the temperature is at your workstation. When the 2 of those are working, the third thing that is happening is our solar chimney. Our solar chimney is a raised ceiling area in the center of our space where the hot air rises and escapes through louvers that also open on actuators, just like our outside windows do, and that releases the heat. So it creates a natural draft of air from the open windows across the workstation and up through the solar chimney, which is a completely passive design.
In this particular case, the building sits on 2 property lines, and we knew that those 2 property lines, because of building codes and adjacencies, we weren't going to be able to open up those facades to allow in natural light. And the good news was that the 2 facades that we could open up were the north and east. And of course, the north facade is going to bring in the best light, diffuse, soft light, and the east is pretty good. We've got a good light in the morning, but we're not getting a tremendous amount of heat gain over the course of the day. And so the south facade and the west facade, particularly the west facade, is the worst. So those being opaque walls that were insulated and not having solar heat gain or radiation coming to the building was perfect. And so from that standpoint, the engineers were kind of starting off on the right foot. So I'd love, as the designer, to take credit for it, but it really had everything to do with the owner kind of buying the right building, and I think that that's a great lesson to be learned. But working together with the engineers, there were a couple of things that we kind of bounced back and forth that really kind of drove the design. And we thought that in the beginning that east facade that could open up upper windows would be great because we do get southeastern breezes in this part of the state. But what we found out from mechanical engineer was that we didn't get enough, and that we were not going to be able to draw enough air through just wind movement through the building. And so that resulted in the thermal chimney design that the mechanical engineer came up with.
An 87-foot-long zinc-clad roof-mounted solar chimney, thought to be the largest of its kind in Arizona, supports the building's passive cooling system. Similar to chimneys constructed in ancient adobe and stone buildings, the solar chimney functions by capturing hot air rising in the office, letting the air escape to the outside through operable louvers located high in the space. This encourages a breeze across the workstations in the office, as fresh air is drawn in through the building's operable windows.
The passive cooling strategies used in this building really are centralized around the thermal chimney, which is the engine of the passive cooling system. The thermal chimney heats up on a typical Phoenix summery day and draws air through the building. That air enters the building through either the operable windows, which are automated, or through the passive shower towers. And that creates a natural cooling in the building and a natural exhaust created by the thermal chimneys.
4 evaporative cooling towers, nicknamed shower towers, work in conjunction with the solar chimney to passively cool the building, generating 16 tons of cooling naturally. Located along the east facade, the towers are able to sense and respond to climatic changes, including wind speed and temperature. Condensate is captured from the building's multiple roof-mounted heat pumps and used as replacement water for the shower towers to augment the potable water source.
The infamous shower towers, the term we sort of made up that is integral to our passive cooling system. So basically it's HDPE pipe, so it's just big plastic pipe, the same stuff that's underground in freeways. And so this is just sort of strapped to the building. And then we built this big duct system in here, so there's no pump in here, there's nothing like that. It's just rocks at the bottom, sort of a catching tray for the water. And at the top, there's a big sort of tower-looking thing that has a ring of misters and 2 shower heads at the top. And so that comes down like I described earlier. And then on each side, you can see where it's ducted directly into the building. And then there's dampers at the window line that open and close at the same time as the windows and the solar chimney dampers. So the whole system kind of runs together. It's all tied into our building management system. So all of those set points and programming, we spent a lot of time writing that program and the sequence of operations to make sure that we were really taking full advantage of the weather when we could.
The shower towers were a very custom design for our space. We knew we wanted some form of evaporative cooling, but we didn't want to put your old school swamp coolers on the outside of our building. One, because they don't provide enough cooling, and 2, they're just not aesthetically pleasing. So we thought, how can we do this in our own way that looks architecturally appealing and also functions well? And so we had our mechanical engineers work together with our sustainability consultant and design these shower towers out of very simple materials. Part of our goal with that design, the shower towers and other designs in the space, is that we did things that were easily repeatable for other customers and clients and owners in the future. And so using very easy to obtain HDPE drainage pipes and typical sheet metal, we built these things, regular shower heads, regular mister rings. It's a residential mister system. And so it was very custom for us, but it's very easy to duplicate.
Another passive strategy employed on the project is adjusting thermal comfort conditions up to 83 degrees in the summertime. In order to achieve this effectively, air movement is applied to help expand the perceived comfort conditions of the space. High-volume, low-speed fans, known as HVLS fans, are utilized throughout the open office area and operate during both passive and mechanical cooling modes.
Air movement can have a dramatic impact on thermal comfort. Air speeds as low as 50 feet per minute can provide a perceived cooling effect. Generally in this kind of environment, in an office type space, we'd see air speeds maybe getting up to 150 to 200 feet per minute, which could give us a 5, maybe even a 6 degree cooling effect depending on conditions. The HVLS fans in this project have several different features that make them unique. The airfoils are designed to efficiently move air, much more efficiently than a flat blade would. It allows them to not be reversed in the winter, so they can actually spin slowly in the forward direction, still circulate the air in the space, push the hot air from the ceiling down to the floor without creating a draft. In addition, the fans use winglets on the end of the airfoils. Those winglets capture the air that would typically slide off the end of the foil and redirect it downward for a useful purpose.
In the morning, when the air is cooler, the fans are turning slow. It has that Casablanca look to it, was the fans are just kind of slowly turning. But as the temperature in the space rises, even if the window is closed, it doesn't mean we necessarily are going to be going to air conditioning. It just means that the air outside can't support the coolness that we're trying to achieve inside. So to achieve whatever cooling we can get is really dependent on the fans operating from a slow speed, and as that temperature gradually climbs in the space, the fans will gradually ramp up to their set point at the highest rate to provide the maximum cooling that they can provide.
Because we knew that from a psychological standpoint, people like to feel air movement. I'm sitting right now feeling air movement in the building from the fans, and it's beautiful, in the building right now, and it's probably close to 100 degrees outside. So they were a big part of how we integrated the building and how we wanted the building not only to feel but also to look. There's an appeasing and aesthetic value with the fans as well, to see the constant movement of the fans moving around at their speeds. And I think it just makes the people that work in the building and the guests very comfortable about the space, knowing that there's a constant breeze and some air movement.
The interesting thing is that when we started the project and we were talking about the idea of using fans in the project, there wasn't even necessarily at that point like a calculation that was done saying, well, we could use that. But the thing that we kept coming back to was, well, how do you live in your own house? And we all have ceiling fans. Ceiling fans are a part of how we live to keep our spaces cool in our own homes. So it was kind of a natural strategy to use in this project.
One of the key concepts in using air movement for cooling is that you need consistent, steady airflow. Something like a oscillating fan where the airflow comes and goes tends to be more disruptive. In addition, if the period between oscillations is large enough, the occupants actually miss that airflow and start to warm up. So providing steady, consistent overhead air movement means increased comfort for the occupants and fewer hot complaints. So we are in Phoenix, and heating is not typically used here, at least not as much as it would be in a northern climate, but there definitely are times of the year where the heating system does turn on. In those times when the heating system is operating, you're basically discharging air high in a space, and you want to push that down to the floor, which is counter to the natural buoyancy of the air. So the fans spin in a forward direction slowly, and they push that hot air downward to where the occupants and the thermostat is located, so that basically you increase comfort while getting increased efficiency out of your heating system. One of the other benefits of elevated airspeed is the perceived cooling effect will allow for a reduction in tonnage. In this project, there was almost a 50% reduction in tonnage because of the passive cooling system. The circulation and air movement created by the fans definitely was a factor in that reduction.
Starting early in design, the team used a combination of building performance models to optimize performance of the systems. This almost instantaneous feedback allowed for more informed decision-making. And, when coupled with other studies such as lighting power density, daylighting analysis, and CFD modeling, made for some outstanding solutions, which are typically eliminated without adequate analysis. Energy modeling was challenging, partly because DPR has a non-traditional office where employees are often away at the job site. The modeling was even further complicated by the passive systems. While airspeed was not included in this energy model, recent changes to ASHRAE 90.1 Appendix G allow for the inclusion of air movement for lead projects.
So we used a combination of softwares to model the energy and the building performance. In terms of energy, because our main focus was building performance and thermal comfort, and by delivering those, we knew that we would be reducing the energy. So the energy modelling became a byproduct of the building performance modelling. We already had a criteria that we were doing 100% daylit building. We were already doing a passive cooling that we knew was a high percentage of the annual consumption, and therefore energy modelling was done in a relatively simple tool. We used Energy Plus and Design Builder and used those in a more simple tool, Energy Pro, where we calculated the energy and used that basic energy calculation for our lead submittal.
EA Credit 1 relates to the energy efficiency of a building, basically comparing your proposed design to a baseline minimally compliant building. The use of elevated airspeed is allowed in the energy models. Basically, you can take credit by increasing your set point and then showing that you can provide a thermally similar or equally comfortable space through the use of elevated airspeed. Using something like the thermal comfort tool from the Center for the Built Environment, you can input in elevated airspeeds and show equivalent comfort to a more traditional HVAC system. Recent changes to the standard do allow for credit for elevated airspeed, and so you can increase the thermostat set point in your proposed design and then offset that increased set point through the use of elevated airspeed. And then in your baseline design, you would basically model a more traditional HVAC system. The difference in the energy consumption between those two would then be the energy impacts that you would see from the air movement created by the circulator fans.
The natural lighting system is the most significant energy-saving strategy used on the building, reducing artificial lighting usage by 90%. Over 82 tubular daylighting devices, or TDDs, are scattered throughout the facility to bring daylight into all the spaces, providing variation in light throughout the day and across seasons. From the inside of the building, the expansive ceiling height and volume within the solar chimney provides a clear story effect, where light from additional TDDs at the top of the solar chimney enters the office space from a high elevation. The natural daylight connects employees to the daily cycle of the sun, entraining their circadian rhythms, relieving stress, and improving productivity.
So in addition to the energy modeling that we did to size our PV system, we also did a lighting model. So we treated our tubes like a light fixture. So they're placed really strategically so that there's an even light level, even though there's no lights on. So through that lighting model, we discovered that we could reduce the number of tubes by 12 on the outside perimeter on the north and east because we have so much light gain from our operable windows. So that lighting model helped us save money, and that was super beneficial in terms of the initial costs, our life cycle costs, and then also just helping to create the balanced light levels.
Because the building's interior is so well lit by natural light during the day, a life cycle cost analysis showed that interior LED lighting was not cost-effective for a 10-year return. However, LED lighting was deemed an ideal solution for exterior site lighting at night, which further reduced energy demands. The occupants of a building have considerable influence on a building's energy performance. By taking on the responsibility of monitoring and modifying their own behavior, occupants are able to actively contribute to the success of a net-zero energy building. One vital component of energy use that occupants can affect is plug load. As system efficiencies increase, plug loads become a critical factor in reducing overall operational energy use. After spending a year evaluating their first net-zero building in San Diego, DPR realized that if they were to be successful in Phoenix, they would need to take a serious look at plug loads. As a result, the team installed a kill switch that is connected to 95% of the non-critical plug loads of the space. The result is a 37% reduction in plug load energy use, and people love hitting the button.
So we're the second DPR office to have built something extraordinary, a LEED Platinum, hopefully net zero building. And so we got to have a little bit of an advantage, lessons learned. And so one of those lessons learned was our nighttime plug loads. So to address that, we installed what we call a vampire switch. We made it a little fun putting a sticker of vampire teeth on there. But basically all this is at the end of the night, the last person out hits the vampire button. There's one at each entrance point. And it shuts down all the non-critical loads. So all the monitors, your power pack for your laptop, anything that we don't need, the microwave, all of that stuff shuts down. We were able to downsize our PV system because of this, and it was super cheap. It probably paid for itself in our first month of energy savings. So super easy for new TIs. Every building should be doing this. It's of all of the amazing features we have here, the most cost-effective one.
It's kind of fun, and it's very interesting to be in the building, especially in the morning, for you can hear the system start revving up. You can hear the printers start. You can hear the monitors turning on. You can hear the operable windows open up, watch the fans start up. The shower towers may turn on. It's a very active building, especially in the morning.
In order to monitor their energy use during the day, a building dashboard was installed. The system displays in real time how the building is performing by comparing the energy production to the energy usage. Anyone can access the dashboard over the web, but employees are granted more in-depth access to a detailed breakdown of data. A prominent kiosk display located at the front desk enables occupants, visitors, and the public to view energy and water use information on touchscreen displays. Comparative graphs and other visualizations make it easy to understand the performance of the building at a glance.
Called the dashboard. The one everybody can see is called the kiosk, but the dashboard is a more detailed, more data-heavy interface that we as building owners and occupants can refer to more often to gather more robust data sets. For renewable energy credits in the LEED rating system, we achieved all 7 of the EA credits, and we achieved innovation and design credit for exemplary performance since we achieved net zero energy. So, LEED goes up to 13% of on-site renewable energy generation, and we got 100%. So, we wanted to try to get a little bit of extra credit for that.
In general, people who go to an office environment, they go do their job, and I think that they have the expectation, or maybe they think in the back of their mind, energy is not my problem, it's the landlord's problem or someone else's problem. And I just think that that information is power. It's like once you know something, it's really hard to not do something about it. One of my friends that works here is saying that he rides his bike in the morning and then showers. And how many of us know how much water we use when we take a shower in the morning, right? But he knows. He'd go right to the dashboard and he could say, oh, I just took a shower and this is how much water I use. But we don't know that. We don't necessarily track that at home or understand that. But when we, as a society, start to understand the resources that we're using, then that facilitates change. I mean, that starts to suggest that we know, and we can't just take it for granted anymore, that, oh my gosh, I use this much water, I use this much electricity. What does that mean? And the dashboard is a tool that communicates that. So I think that's just fantastic.
A 78.96 kilowatt photovoltaic array is installed over the parking canopy system. PV Watts, a free online tool provided by the National Renewable Energy Laboratory, was used to determine the energy production and cost savings for the grid-connected PV array. In addition, a 4,500-watt solar thermal system provides hot water for the building. This closed-loop glycol system has an 85-gallon capacity tank and 2 collectors on the roof of the building.
We achieved all 7 of the energy and atmosphere on-site renewable energy credits through the LEED rating system, and we also achieved another credit for exemplary performance in the innovation and design credit.
Sizing the systems and understanding what the loads were in the building was probably one of the biggest challenges that we had on the technical side, because as we would come up with one solution for one thing, it might mean we drove up the electrical requirements, which means the PV system had to go up. But then as we realized, well, we're not going to use lights during the day, that drove down the electrical requirements. So the PV solution was actually one of the last solutions that we came to as we finished the project, because until we finished all the layout and understood where all the people would be, how many tubes we'd have, how many desks were going to be in the space, and how many conference rooms there were going to be, what lights could be on, what wouldn't be on, what would be LED, what would be fluorescent, all those decisions that went back and forth. We were designing well into the construction process. We were still making decisions while we were, putting drywall in. We were still trying to decide the lights and configurations that ultimately drove the size of the PV system. I don't remember the exact numbers, but I remember at one point we were, in the 130 kW size, and we were down in the 50 kW size, and ultimately ended up, I think, around 78 kW, which is, big swings. But when you talk about changing loads dramatically by use of technology and reducing load by not running the air conditioning because we have our fans and running our building at a higher temperature than what we're used to, it's all those unknowns that we had to work through to get to those solutions.
So we had done multiple analysis on the angle of the PV to maximise it. Phoenix being a very hot environment, it was certainly a disadvantage for us to try to maximise the PV during the summer season. In fact, it was far better us protected them from the heat gain rather than try to focus them on there. The angle of the PV was determined more as an annular basis rather than a summer generation. It was kept away from the shaded zones and provided shading for parking where we thought it was best suited.
In order to earn Net Zero Energy Building Certification from the Living Building Challenge, the requirements of 4 imperatives must be met in addition to achieving net zero energy operation over a year. 1. Limits to growth, in order to curb the building's contribution to the effects of sprawl development. 2. rights to nature, to ensure that the building does not preclude another building from achieving net zero energy as a result of excessive shading. 3. Beauty and spirit. 4. Inspiration and education. These imperatives underscore the notion that renewable energy systems can be incorporated into a building in ways that are attractive and inspiring.
The Living Building Challenge is really a philosophy and an advocacy tool. It's really a way for projects to kind of step beyond the LEED process and show us kind of a stronger commitment to green building and sustainability. But to me, the relationship between LEED and the Living Building Challenge is kind of one of progression. LEED really becomes kind of that entry point for a lot of people to understand what sustainability means for their organization and for their built environment. And really, you can kind of push yourself as you get more and more familiar with LEED. You can kind of push yourself towards those higher levels of gold and platinum certification. But really, the next step becomes almost kind of a mind shift for people, because it forces them to think beyond the platinum stage and really find how the built environment and the natural environment start to coexist. And it's really about taking all of those principles and occupant engagement and kind of an understanding of kind of the ecological place that we exist and how to fold that into a nice cohesive built environment. That's a much larger shift, and you usually see that come out of people who have already gone past the platinum or introduced themselves to the platinum stage several times. Only then do they kind of say, well, how do we start to take this further? Well, net zero was a goal originally for DPR. They had experienced a little bit of that with their San Diego office, and in the pursuit of that, made that a very clear goal from the beginning for the Phoenix office. Over the course of that process, net zero had always been a goal, but the certification wasn't. And so it was after we had achieved the LEED Platinum certification that I asked whether or not we really wanted to try and push for that net zero energy building certification. Net zero energy is a kind of a subset of the Living Building Challenge certification, or Living Building certification. The Living Building Challenge is comprised of 20 imperatives. In order to achieve net zero energy on a project, it's because the Living Building Challenge, both the net zero certification and the Living Building certification are both performance-based. You have to go through a 12-month period of understanding your building and documenting proof that you've achieved it. So we had to go through from, originally we started from December of 2011 to December of 2012, and then ultimately just decided to do all of 2012 as our reporting period. So we had all the documentation for that reporting period, and had already demonstrated in our minds that we had achieved at least the energy component of their requirements.
HVLS fans can help in achieving increased ventilation in a space by helping to mix the air. When performing calculations for the outdoor air intake flow per ASHRAE Standard 62.1, there is a factor for zone air distribution effectiveness. This factor accounts for how good of a job the HVAC system does at getting the outdoor air into the breathing zone where the people are. If the system provides a well-mixed space, then less outdoor air intake is required. However, if there is stratification of the air, as is common with overhead distribution systems, then more outdoor air intake flow would be required.
This is for the most part, a passively ventilated building. We have 100% outside air passing through the building at any given time, and the amount of air ranges from about 18,000 CFM to 23,000 CFM. And so air quality is as good as the air quality we're receiving outdoors at any time. We don't recycle, in passive ventilation mode, we don't recycle air at all. We have a fully designed HVAC system, and that HVAC system also has increased outdoor air ventilation. We exceeded the 30% above ASHRAE requirement required by LEED. We also have economy cycle on the units, although they're undersized for the code requirement. Every unit has economy cycle and operates in outside air mode very often. We started the design process in the San Diego office, and we were developing CFD models on the airflow from cool air entering into the building at low level and warm air exiting the building at high level. And in that process, it's really about stratification of the air. Our goal originally was to create stratified air so that we could exhaust the warmer air out through the high levels. Probably halfway during the design, DPR approached us with the idea of using fans to assist the thermal comfort. And so we modelled those fans by increasing the velocity of the air in the space. And the impact of that is that we limited the stratification and mixed the air. It was our original concept that we wouldn't do that, and I originally recommended that we didn't do it. However, after modelling and now after a year of occupancy, there is no doubt that adding the fans and mixing the air is a far better addition to thermal comfort than by stratifying it.
ASHRAE Standard 55 plays a significant role in a couple of LEED credits. The primary ones would be the indoor environmental quality credits related to thermal comfort. Air movement can provide a significant cooling benefit, making occupants feel much more comfortable, cooler during the summer months, even though set points can be as high as the 83 to 86 degrees that are typical in this project. Thermal comfort in the summer is taken care of by elevated airspeed. In the winter, there is a concern about draft, especially with overhead circulator fans running. It's important that you have a fan that with the air movement in the space, you not exceed 30 to 40 feet per minute, which is where draft can occur. Whatever your air distribution strategy is, you need to make sure to maintain good air mixing in the space without creating a draft, which means keeping air speeds below 30 to 40 feet per minute at the occupant level. In projects that use large overhead fans for air circulation, that typically means slowing them down to a speed where they're going to still sufficiently mix the air in the space, but doing so without creating a draft.
The DPR office did not attempt to achieve the thermal comfort credit in LEED. However, the concept of thermal comfort drove many decisions in the project, including the selection of the HVLS fans. At the same time, the occupants were called upon to adapt their thermal expectations so that they would align better with the natural environment.
Occupant engagement, I think, played a significant role in terms of DPR meeting their net zero energy requirements. I really think that it's kind of the third level of engagement. You can do the reduce and the reduce level of things and try and make things as efficient as possible. So you have the eliminate the need first, and then you have reduce the need second. And then the last piece is really that engagement piece, which kind of shatters our preconceived notions of a space, where we're not entitled to 74 degrees all the time. It really forces us to say, well, we're going to live within a different threshold.
When occupants find themselves living in a naturally ventilated building, they naturally increase their tolerance. You'll find that over the past year, the occupants here are far more tolerant than if they had have been in an air-conditioned building.
DPR had other locations in Southern California that were very similar to this, and we wanted to improve it. So they challenged their employees and the guests of the building to let them know that we're going to be expanding on the norms of a building. So possibly wear a light sweater or dress a little lighter, depending on whether heating or cooling. You should prepare yourself for that. That information was invaluable to the team, knowing that already DPR had educated their internal audience, which would made it a lot easier from a design standpoint to know that we're going to deliver a system that's going to do that.
The building is set for around 83 degrees before it goes into cooling mode now. Many people think that that's too warm. Now, of course, people who live in Phoenix are acclimatized, and 83 degrees is a very comfortable temperature. In San Diego, we run it to 81 degrees, where, us San Diegans, our tolerance isn't as high as people who live in Phoenix. Although, we have been on a path of increasing that temperature. We started at 79 in San Diego, and now we're up to 81, and that's really about the occupants, becoming acclimatized to the environment they're in.
So as far as occupant engagement goes within our space, we designed all of our systems to work autonomously. There's temperature sensors, there's sensors that are tied into the weather station at the airport to make sure that all of our systems are working in their passive mode appropriately. So we designed that so our occupants wouldn't have to be switching switches all day long. A way that we did become engaged and that we will continuously be engaged in our building throughout its life is continuously tweaking the way that it operates. In our first year of operation, for example, in the wintertime, the windows were coming open more than we would have liked. They were letting in too much cold air, and as a result, our package units were coming on and we're using electricity to heat the space. That was one of the first tweaks that we had to do to our building management system, and we find that we're consistently making modifications to the sequence of operations so that it works more efficiently and it creates a more comfortable space for our building occupants.
We have quite a complex building management system on the building. So I would have to say that, from a passive standpoint, we have low-tech heating and cooling that is augmented with some heat pumps, more high-tech, but a very high-tech system that makes it communicate and brings the whole thing together, not just mechanically, but electrically as well, water consumption-wise as well. Intuitively, the building knows how it needs to act based on the actual weather outside. There's actually a weather station on the building as well, and the weather station reports back to Sky Harbor, so we'll know things like outside ambient temperature, Fahrenheit, humidity, wind speed. We'll know if there's wind warnings, if a monsoon's coming up, so the building will know when to open dampers on the solar thermal chimney or close windows on the motorized operated windows. All of this information is trend logged into the system front end, and there's a data log of that. And by reading that and going through that, again with the engineering team and the commissioning team, we can fine-tune the building. And as DPR brings more and more empirical data forward, how many people were in the building on this day? Were there any issues on this day? Certain months of the year, we take all the information, we review it, and we analyze it, and we can then take the parameters of the building and adjust them through the front-end system. There's a dashboard component, a graphical dashboard component on the system that allows us to actually visualize what it is, not just looking at data, but you can look at a screen and see consumption that's happening actually at that point in time. Whether it's water consumption, electrical consumption through plug loads or energy consumption, we can see it all at one time. So the process is going to continue to evolve, and I believe we will continue to fine-tune the parameters of how the building thrives within its own environment with the inhabitants, because the inhabitants change. Return on investment, less than 10 years. Minimum net zero. What I use is what I give back, is what I have, or give back to the grid. Those have all been achieved, and I believe we'll continue to fine-tune that to have better results.
What's been the best outcome of this kind of post-occupancy evaluation and going through the net zero energy certification is you have to kind of quantify what all of the values mean. And it allowed us to really kind of look at what the predicted energy load was versus the actual energy load. And you really start to see the impact of that passive strategy show up. So if we could start doing that on more projects, I think then we start to get to a point where we could start to quantify what those values are a lot easier and make those estimations maybe more informed than anecdotal.
There's been some tough times. We've had to learn how to adjust the system. Initially, we started at, I think, at 64 degrees for heat, which means that people were coming in wearing jackets and gloves and hats inside the building. And one time when I came in and I could see my breath when I was talking to somebody inside the building, I said, it's time to bump it up a couple degrees. And so, but it was a live and learn, and everybody was part of it. They became just as engaged in helping us achieve those goals rather than sitting back and complaining about it. I know know that there were conversations of people not liking certain things, which I totally understand and am okay with, but we wanted it to be a proactive conversation of what's working and what's not. We got great feedback from people, which helped us tune the building up, and we're still learning today. The building's actually working more efficiently in the second year than it did actually in the first year, which we've managed to make more energy with our photovoltaic system and use less energy with our cooling and other things this year. So it's been a time of change for a lot of people, and it's allowed us to understand how people can interact with each other through challenging times like that.
Lessons learned would be to absolutely operate in an integrated team from the beginning. The more you can do as a team, I know it might even sound cliche, but if you want to achieve something that is way outside the box, you want to achieve something in a tight time frame, it is absolutely necessary to have everybody on board as soon as you possibly can.